Alright, so now that we are familiar with drawing structures, meaning where do we place those bonds and where do we place the lone pairs or non-bonding pairs, we can actually now assign specific geometries or shapes to these compounds. And this is just like learning shapes when we're young, as triangles or circles or squares and rectangles, and we learn those by not only seeing what they look like in terms of visualization, but also we're given some guidelines, such as a three-sided figure, of course, is a triangle. And then as we get older and we take more classes, we learn specific kinds of triangles, like isosceles triangles and right triangles, and so on and so forth. And we're given obviously specific criteria so that when we look at a three-sided figure, we not only know that it's a triangle, but then we have additional factors that we can take into consideration to help us to classify it as a specific type of triangle. And we're going to do the same thing here. And we're going to use what we call the valence shell electron pair repulsion model or theory, which is VSEPR as an acronym, and it is going to help us in determining the shape of a particular compound. And we can identify the shape either specifically, like triangle, or even more specifically as, for example, a right triangle or an isosceles or equilateral triangle. So we can basically increase the level of specificity. So we can basically say that the arrangement is the more general shape and the geometry is the more specific shape. Again, just like saying triangle versus right triangle. Alright, so let's take a look at some guidelines that will help us in determining the arrangement and geometry. And it's very important to make a distinction between those two terms. Alright, the first thing we're going to do, of course, is draw our Lewis structure, because that's the first thing we need to do to determine the shape of the compound. Once we do that, we're going to look at the number of electron domains. And when we discuss VSEPR theory, we call electron pairs electron domains. So a domain is basically an electron pair. And we count all of them for the central atom. Again, this is just for the central atom. The geometry is always from the perspective of the central atom. And what we're going to do is count the total number of electron pairs or domains on the central atom only. And that means whether they're bonding domains or pairs or non-bonding pairs or domains, we're going to count everything. Once we have the total number of electron pairs or domains, both bonding and non-bonding, and we get the total, we can look up the total on a table and it will tell us what the arrangement is, the general classification. And this is what we mean by that. This is the table. So total number of domains for us can be 2, 3, 4, and of course up to 6. And this table we're just going to show up to 4, but they can go up to 6. And this tells us that the general arrangement. Once we have the general arrangement, then we're going to look specifically to see exactly how many pairs were bonding pairs or domains, how many were bonding, meaning involved in a bond, a straight line connecting the elements, and how many of those domains were actually non-bonding or lone pairs, the dots on the central atom. And looking at that specific combination, we can look up the geometry on the table. So a quick outline here. Draw the Lewis structure is the first step. Count the total number of electron domains, bonding and non-bonding. Classify the arrangement, meaning just this category. Then within that arrangement, so let's say within tetrahedral, we have a combination of 4 bonding, 0 non-bonding to add up to 4. Still total of only 4 domains. Another combination to make 4 domains would be 3 could be bonding and 1 could be non-bonding. That still makes 4 total domains. Or you could have 2 of them bonding and 2 of them non-bonding. That would still be a total of 4 domains. So once we have the arrangement, we can look within the arrangement and within that arrangement find the specific combination. So if we have a 3-2 combination, it will be tetrahedral in arrangement, and then for 3-2 it's a trigonal pyramidal geometry. So we can determine the specific geometry for the central atom. that will also help us determine the bond angle, and here you have some examples. Now the other thing I also wanted to point out is not only is the geometry with respect or about the central atom, but also when you look at the central atom and it has multiple bonds, meaning double or triple bonds, still count as only one domain. And that's why we call them electron domains and not necessarily pairs in the VSEPR model. If you have, let's say, a double bond, like in the example of, let's go back up here to carbon dioxide, our central atom would be carbon. It has a double bond on one side, another on the other. So it has two double bonds. That's two bonding domains. I don't see any dots on it, so it has zero non-bonding. So again, even though you see 4 bonds here, they count as 2 domains because they're multiple bonds. It's a double bond, singular, not double bonds, plural. So it's 2 bonds that happen just to be double in nature. So 2 bonding domains, I don't see any dots, so 0 non-bonding domains. So that's a 2-0 combo, a total of 2, and the only combination there is 2 0, so it would actually be linear, okay, for arrangement and geometry in a 180-degree bond angle. Looking at something like H2O here, where you have the oxygen being the central atom, it has 1 bond to the left, 1 bond to the right, so that's 2 bonding domains. And right on the oxygen you can see that there are 2 lone pairs or non-bonding domains. So that's a total of 4. 1 line, 2 sets of dots. 1, 2, 3, 4. 4 total domains means I'm in the 4 category. The tetrahedral arrangement and a specific 2 bonding pairs, 2 non-bonding pairs or domains would be a 2-2 combo, making it have, yes, a tetrahedral arrangement, but a bent geometry and a bond angle of 105. So again, it's very important to make sure that you're counting both the bonding and non-bonding domains. Recall the multiple bonds are still 1 domain. Just for the central atom, look up the total number of domains, determine the arrangement, then within the arrangement, the specific one could be the geometry. And again, some bond angles will follow. And again, we can go up from all the way up to 6 total domains. This table, of course, for the purposes of this tutorial, will go up to 4 depending on your course. You may be subject to the full table or just this abbreviated table, but this should give you a better understanding of how we can determine the shape of a particular compound based on its Lewis structure. And that's why it's so imperative that you draw the Lewis structure correctly, because if you don't draw the structure correctly, then you may have the wrong number of bonds and bonding domains and non-bonding domains, and then select the wrong arrangement and geometry. So double check your structures before beginning this exercise of determining arrangement and geometry.